Introduction to MuSig. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are taking a deep dive into MuSig, a groundbreaking multi-signature scheme built upon the elegant foundation of Schnorr signatures. A multi-signature, or multi-sig, protocol allows a group of people to collectively control a single asset or authorize an action. Instead of one person signing off, you might require 2 out of 3 or 5 out of 7 participants to agree. MuSig is a specific protocol that enables this functionality in an incredibly efficient and private way. It allows multiple participants to combine their public keys into a single, aggregate public key, and then collaboratively create a single Schnorr signature that is valid for that key. The final result is a transaction that looks identical to a standard, single-signer transaction, which has profound benefits for both privacy and scalability. In this presentation, we will explore why simple signature aggregation is not secure, how MuSig solves this problem, and we will walk through the entire interactive signing protocol step by step. Recap. The power of Schnorr signatures. Before we can understand MuSig, we must recall the magic of Schnorr signatures themselves. The key property that makes MuSig possible is linearity. As we have learned, the Schnorr signature equation, S equals K plus E times X, is a simple linear equation. This means that if you have 2 signers, you can add their public keys to get a new valid public key, and you can add their signatures together to get a valid signature for that combined key. This works because of the underlying properties of elliptic curve scalar multiplication. Adding the private keys x1 and x2 corresponds to adding the public key points p1 and p2. This algebraic simplicity is what opens the door to multi-party computation. However, as we are about to see, just naively adding keys and signatures together opens a huge security hole. MuSig is the formal protocol that harnesses this linearity while closing that security hole. The naive approach and why it's insecure. So, if Schnorr signatures are linear, why can't we just have everyone create a signature and add them all up? Let's consider the simplest possible approach. Imagine Alice and Bob want to create a 2 of 2 multi-sig key. The naive idea would be for them to simply add their public keys together to create an aggregate key. P_AGG equals P1 plus P2. To sign a message, they would both sign it and add their responses. S_AGG equals S1 plus S2. This seems like it should work, but it suffers from a fatal flaw known as the key cancellation, or rogue key, attack. As the slide demonstrates, a malicious Bob can trick Alice. Instead of generating his key honestly, Bob waits for Alice to publish her public key, P1. He then crafts a malicious public key, P2, which he calculates as P_rogue minus P1, where P_rogue is a key for which he knows the private key. When they create the aggregate key, P_AGG equals P1 plus P2, the P1 and minus P1 terms cancel out, leaving just P_rogue. Bob can now sign for this aggregate key all by himself, without Alice's consent or knowledge. He has effectively stolen control of the joint account. This attack proves that we need a way to ensure every participant honestly controls the private key for the public key they claim to own. MuSig to the rescue. Key aggregation done right. MuSig is the solution to this rogue key attack. Its core innovation is a secure key aggregation step that forces every participant to prove they know the private key for the public key they are contributing. It prevents a malicious actor from using someone else's public key in their own calculation. It achieves this by making the aggregate public key a weighted sum of the individual public keys, rather than a simple sum. Each public key PI is multiplied by a unique challenge factor CI before being added. This challenge factor is derived from a hash of all the public keys in the group, plus the specific public key of the participant. As you can see in the comparison on the slide, the naive approach is just P1 plus P2. The MuSig approach, however, is C1 times P1 plus C2 times P2. Because the factor C1 depends on P2, and C2 depends on P1, Bob can no longer craft a key that cancels Alice's key out. He doesn't know what his challenge factor will be until Alice has committed to her key, and vice versa. This interdependency is what stops the attack and ensures the aggregation process is secure. MuSig key aggregation. Step by step. Let's walk through the secure key aggregation process in detail. Suppose Alice, Bob, and Carol want to create a 3 of 3 multi-sig key. First, they all share their individual public keys, P sub A, P sub B, and P sub C, with each other. The second step is to create a common reference value that includes all participants. This is done by hashing the concatenation of all the public keys together. We'll call this hash LL as a commitment to the exact set of keys participating in this specific aggregation. Now, for the crucial step, each participant calculates their own unique challenge factor, C sub I. Alice calculates her factor, C sub A, by hashing L along with her own public key. P sub A. Bob does the same with his key, P sub B, and so on. Finally, the aggregate public key, P sub AGG, is computed as the weighted sum you see in the code block. It's Alice's factor times her key, plus Bob's factor times his key, plus Carol's factor times her key. The resulting point, P sub AGG, is the single public key that represents the entire group. This key can be published and used for verification, and it looks just like any other public key. The MuSig signing protocol. Round 1. Commitment. Now that the group has a secure aggregate public key, how do they sign a message? This requires an interactive, multi-round protocol. The first round is the commitment round, which is very similar to the first step in a standard Schnorr signature. Each participant, Alice, Bob, and Carol, must independently generate a secret, one-time use nonce. Alice generates KA, Bob generates KB, and Carol generates KC. It is absolutely critical that these nonces are chosen randomly and are never reused. Using their secret nonce, each participant computes a public commitment point. Alice computes RA equals KA times G, Bob computes RB equals KB times G, and so on. This is their public commitment to their secret nonce. The sequence diagram on the slide shows this first step. They each generate their secrets, and then they broadcast only their public R points to all other members of the signing group. At the end of this round, everyone knows everyone else's public commitment, but no one knows anyone else's secret nonce. The MuSig signing protocol. Round, aggregate R and challenge. The second round of the protocol is straightforward and doesn't require any interaction. Once every participant has received the public commitment points RA, RB, RC from everyone else, they can all independently perform the same calculations. First, each person computes the aggregate commitment point, RAGG. This is done by simply adding all the individual R points together. Because elliptic curve point addition is commutative and associative, everyone will arrive at the exact same RAGG point. Next, everyone computes the global challenge, E. This is a hash that binds the signature to the specific keys, message, and nonces being used. The input to the hash function is the aggregate public key PAGG, the aggregate commitment point RAGG, and the message M. Again, since everyone has the same inputs, they will all independently calculate the exact same challenge value E. At the end of this round, all participants share a common aggregate commitment RAGG and a common challenge E. The MuSig signing protocol. Round 3, partial signatures. This is the final interactive round, where each participant creates their piece of the final signature. This piece is called a partial signature. Now that each participant has the global challenge E, they can compute their own partial signature, SI. The formula, as shown on the slide, is very similar to the standard Schnorr response formula, but with one key difference. Alice calculates her partial signature, SA, by taking her secret nonce Ka and adding the product of the global challenge E, her unique key aggregation challenge factor Ca, and her private key Xa. Bob and Carol do the same using their own secrets and challenge factors. This step proves that each person possessed their respective secret nonce and secret private key. Once they have calculated their partial signature Si, they broadcast it to the other participants, or to a designated aggregator who will assemble the final signature. Creating the final signature. The final step is the simplest of all. Once a participant or an aggregator has collected all the partial signatures, SA, SB, SC, they are combined into the final aggregate signature scalar, SAGG. This is done by simply adding all the partial signatures together, modulo Q. The resulting single scalar SAGG, paired with the aggregate commitment point RAGG from round 2, forms the complete MuSig signature. The beautiful thing about this final signature, RAGG, SAGG, is that it is a perfectly valid Schnorr signature for the aggregate public key PAGG. It has the exact same format and size as a signature created by a single person. There is no way for a third-party verifier to know that an interactive, multi-party protocol was used to create it. All the complexity of the multi-signature scheme is completely hidden. Verifying a MuSig signature. One of the most powerful features of MuSig is the simplicity of verification. A person verifying a MuSig signature does not need to know about any of the multi-party complexity that went into creating it. They do not need to know the individual public keys, the individual nonces, or anything about the three-round protocol. The verification process is exactly the same as verifying a standard, single-party Schnorr signature. The verifier takes the aggregate public key PAGG, the message M, and the final signature RAGG, SAGG. They use these inputs to check if the fundamental Schnorr verification equation holds true. They calculate SAGG star G on the left side, and RAGG plus H parenthesis PAGG or RAGG or M close parenthesis star PAGG on the right side. If the resulting points are identical, the signature is valid. This means that systems that are already built to handle Schnorr signatures can verify MuSig signatures without any changes to their verification logic. The complexity is entirely handled by the signers. Proof. Why MuSig verification works. Let's quickly walk through the algebra to prove that the standard Schnorr verification works for a MuSig signature. We start with the left-hand side, SAGG times G first. We substitute the definition of SAGG, which is the sum of all the partial signatures SI. So we have S1 plus S2 plus ... times G using the distributive property. This becomes S1 times G plus S2 times G plus ... Now, for each term, we substitute the definition of SI, which is Ki plus E times Ci times Xi. This gives us a sum of terms that look like Ki plus E times Ci times Xi, times G. We can distribute the G again, which gives us Ki times G plus E times Ci times Xi times G. Now, we can group all the Ki times G terms together and all the E times Ci times Xi times G terms together. The sum of the Ki times G terms is just the sum of the Ri points, which is RAGG. For the second group of terms, we can factor out the common challenge E. This leaves us with E times the sum of Ci times Xi times G. We know that Xi times G is just the public key Pi. So the sum is E times C1 times P1 plus C2 times P2 plus ... And that expression in the parenthesis is exactly our definition of the aggregate public key, PAGG. So, the whole expression simplifies to RAGG plus E times PAGG, which is the right-hand side of the verification equation. The math holds perfectly. MuSig advantages and applications. The benefits of using MuSig are significant. The primary advantage is privacy. Because a MuSig transaction looks identical to a single signer transaction, It's impossible for an observer of a public ledger, like a blockchain, to know how many parties were involved in a signature. A 10 of 10 multi-sig looks the same as a 1 of 1. This is a huge privacy improvement. The second major benefit is efficiency. A single aggregate signature takes up far less space than storing multiple individual signatures. For a blockchain, where block space is a scarce and valuable resource, this is a massive saving. It also reduces the computational load on verifiers, since they only need to perform one verification operation instead of many. The primary application for this technology is in cryptocurrencies like Bitcoin. The Taproot upgrade specifically enabled the use of MuSig to make multi-signature wallets and complex smart contracts more private and less expensive to use. This makes the entire system more scalable and powerful. Summary and conclusion. In this presentation, we have seen how MuSig provides a secure protocol for creating Schnorr multi-signatures. We started by understanding that the naive approach of simply adding keys is vulnerable to the critical rogue key attack. We then saw how MuSig solves this by introducing challenge factors to create a secure, weighted key aggregation scheme. We walked through the interactive, 3-round signing protocol where participants exchange commitments, calculate a global challenge, and produce partial signatures. The beauty of MuSig is that this complex interaction results in a single, standard Schnorr signature. This signature is compact, efficient to verify, and completely obscures the fact that multiple parties were involved. MuSig is a masterful piece of cryptography that unlocks the full potential of Schnorr signatures, enabling systems that are more private, scalable, and secure. Thank you for your attendance. Please consider subscribing to the channel.